Hello guys, so we're going to be covering section 3.6, which is derivatives of logarithms. Some of you guys mentioned to me before in class, and we talked about it, but we said it was okay for me to just write down the notes beforehand, that way I don't have to write them out. You don't have to go through the painful process of me just, watching me write something. So as you see, I have everything pre-written so far, so as I go underneath them, or as I let's see, could I underline? I might underline what I'm talking about, but I think I would prefer just to stick with other things, just as I normally do in class, and underline, that way it's easier for me to erase. But, let's go ahead and get started. So the first thing we're doing is, we're going to be trying to find what a derivative of a logarithm is. So, we've done some functions already. We've done implicit differentiation. We've done we haven't done exponentials. Yeah, we've done exponentials. But we haven't done logarithms yet, just general logarithms. So let's find out, what happens if y is equal to log base a of x, where a is greater than 0, using implicit differentiation. So, if y is equal to log base a of x, then that's the same thing as a to the y is equal to x. So what we can do is take a derivative of this expression right here. And that's how we're going to get, d of dx of a to the y is equal to d of dx of, just d of dx of x. So remember, using implicit differentiation, you kind of have to do the derivative of the inside function. So your inside function be a to the y, or a to the x. So the derivative of that will just be a to the y ln of a, and then you have to multiply by the derivative of the inside. And so the derivative of y is just dy dx. And we have that's equal to 1. And the reason why that's equals to 1 is just because d of dx of x is just 1. So now we have an expression with, dy dx in it. So all we have to do is just, solve for dy dx. And this is what we get right here. 1 over a to the y times ln of a. But a to the y, that's equal to x. So you can just plug that in instead. So we get dy dx is equal to 1 over x ln of a. And this is precisely basically what it says. The derivative of log base a of x is equal to 1 over x times ln of a. And likewise for the natural logarithm, and this is the one you would probably want to remember, is just ln of x is equal to 1 over x. And I have this thing I like to say whenever I'm trying to find the derivative, but we'll get there when we kind of get close. Especially when we do the chain rule. So we're going to differentiate the following, because, once we have these rules, we're going to do some examples. So we're going to do y is equal to ln of x times cosine of x. So we get y prime will be equal to, remember this is going to be the product rule, so product rule, fg prime is going to equal to f prime g plus f g prime. So you keep one the same, take a derivative, then you add the vice versa of that. So here we're going to keep ln of x the same, times cosine of x prime, so take a derivative there, plus ln of x, so the derivative of ln of x times cosine of x. So derivative of cosine of x is negative sine of x, so I got negative ln of x sine of x. Derivative of ln of x is 1 over x, like we just showed. So we get 1 over x times cosine of x, and then lastly we get negative ln of x sine of x plus cosine of x over x. So, that's pretty nice, honestly. It's pretty easy, it's not too bad. So let's do y is equal to ln of x cubed plus 1. Here you'll actually have to use the chain rule because typically you have the function ln of x, but here you have x cubed plus 1 on the inside. So we're going to use the chain rule where u is equal to x cubed plus 1 and y is equal to ln of u. That way y is equal to ln of, u, or ln of x cubed plus 1. That's basically what happens when we get the composition. So likewise with the chain rule, when we try to use, Leibniz notation, we use the dy dx. So we get dy dx is actually equal to dy du. So the derivative of the outside times the derivative of the inside, which is, du dx. So the derivative of, dy du is basically just taking this, take a derivative with respect to u. So ln of u, that's 1 over u. And then when we find du dx, I'll just be equal to 3x squared, because that's just the power rule. Bring down the 3, subtract by 1. But we're not using that just yet. So we have 1 over u times du dx, because all we did right here is plug in for that. And then lastly we're going to have to do is plug in for u. So remember that u is equal to x cubed plus 1. So we have to plug it in right here, and we have to plug in for du dx. So we get 1 over x cubed plus 1 times 3x squared is equal to 3x squared over x cubed plus 1. So that's our final answer. So this one, is kind of gives you a formula how to do many different kinds of derivatives. Especially when we get into more complex, complex structures such as logarithmic differentiation. But so far I like it. It's so far so good. So in general, when we try to talk about if we have a what we did here, we had x cubed plus 1. So we actually have just a general rule for whenever we have a function inside of ln of x. So remember, in general, we have d of dx of ln of u is just equal to 1 over u. But if u is actually equal to some function of x, in this case, u is equal to x cubed plus 1, or it could be equal to cosine of e to the x, or just whatever. It's just a function of x. Then what we get is d of dx of ln of u is going to equal to 1 over u times du dx. Because remember the chain rule, you take a derivative of the outside, evaluate it at the inside, and then you multiply by the derivative of the inside. So if u is equal to g of x, basically what that gives us is the same thing as we have right here. So d of dx of ln of g of x is equal to 1 over g of x times g prime of x is equal to g prime of x divided by g of x. And I actually have a way to say this that I talk to myself or tell myself all the time. And I literally do it whenever I do these derivatives, because a lot of times, if it's clear what it is, and or if it's fun, if it doesn't require a lot of brain work, it's fine. But if something is if g of x is complicated, then this is what I'll do in my head to make sure I understand everything properly. So I usually call the inside the argument, because ln, if you were just write ln like that, you have to have some argument there. So I always just call that again the argument. So what I say, the derivative of ln of g of x is 1 over the argument, so 1 over g of x times the derivative of the argument. And actually, I find that pretty helpful, especially when we get to more complicated cases, which I'll kind of show you whenever we get there. So, let's differentiate the following. Y is equal to ln of 1 over x. So again, that's going to be 1 over the argument, so 1 over 1 over x, times the derivative of the argument, so times 1 over x prime. So try to make that prime. Times x to the negative 1 prime. So remember that 1 over x is equal to x to the negative 1. So when you take a derivative, you just use the chain rule. So prime, you just bring down that negative 1, subtract by 1, and then this is what you get. So when you simplify, this is actually just, here you have x to the 1. So you just get x to the negative 1. So this is why this is down here. And you have the negative, so it goes equal to negative 1 over x. Also, there's a quicker way to do this, and this is one of the things about logarithms which are pretty nice, is that you can use the properties of logarithms before you take the derivative. So likewise, how we just said here that 1 over x is equal to x to the negative 1. So that means we have ln of x to the negative 1. And then we can just use the properties of the logarithm where we can bring down that exponent. So we get negative ln of x, and then whenever we find y prime, we could just do the negative. Derivative of ln of x is just 1 over x. So y prime is equal to negative 1 over x. So, that's just one way we can do the problem. There's many different ways. If you do it this way versus the way I just did it, is okay. As long as you're correct and you make sure every step you do is valid, then you're fine. So the second example we're going to do is, f of u is equal to u plus ln of u. Here we're going to have to use just just like, the quotient rule. So the top is going to be u, and the bottom is going to be 1 plus ln of u. But, I have like a mnemonic device or like mnemonic thing I always do whenever I try to read it. I'm like, low d high minus high d low all over low squared. So I'll keep this in mind. This will be low, and this will be high. And remember that d just means like your derivative. So it's going to be low, so 1 plus ln of u, d high, so d u, so d high, which is u, it's minus high, so minus u, d of du of, low, so 1 plus ln of u. Then all over low squared. So then right here, all I did was just take the derivative now and simplify. So d of du, that's just equal to 1. d of du of 1 plus ln of u, that's just going to be 0 plus 1 over u. So I get 1 plus ln of u minus u times 0 plus 1 over u. And then whenever you simplify that, you just get 1 plus ln of u, and this is just negative u times 1 over u to just equal to negative 1. So you get 1 plus ln of u minus 1 divided by 1 plus ln of u squared, which lastly just equals to this. So, again, this problem isn't so bad. It's just kind of knowing the derivative of the logarithm now, knowing that formula that you have, and just applying it. So the third one is going to be, f of x is equal to the ln of the absolute value of x. So this is kind of different because, ln of x itself is only defined when x is greater than 0. So if we have the absolute value of x, it's defined everywhere except for x is equal to 0. And remember, this is how we define the absolute value of x. It's basically equal to itself if it's positive. If it's negative, then it's the negative version of itself. So what that tells us about f of x is, is that, ln of x is equal to the ln of the absolute value of x is just equal to the ln of x when x is greater than 0. But if x is less than 0, what we get is just ln of negative x. So you may keep this in mind when we find the derivative. And with the way we find derivative of just piecewise functions is just take a derivative of the pieces. So derivative of ln of x, that's just 1 over x. The derivative of ln of negative x is kind of like what I said before, 1 over the argument, so 1 over negative x, times the derivative of the argument, so negative 1. And these negatives will cancel, leaving you just, positive 1 over x. So what I got here, so just 1 over x whenever x is greater than 0, and 1 over x when x is less than 0. So thus, f prime of x is just equal to 1 over x. And you note that we can actually write it like this now instead of writing it as like a piecewise function, because, even like if you have just like, like we only write it piecewise like this, and we don't really need to talk about the domain. Because, in terms of the domain is kind of implied by the kind of function it is, so you don't really need to specify it. And so whenever you write it into just a single form, when you go from piecewise to just a single expression, then you don't really need to specify where x is anymore, since it's just equal to the same thing everywhere. And remember that x still can equal 0. So what this tells us is that, d of dx of ln of the absolute value of x is just equal to 1 over x. So we will keep that in mind whenever we want to do integrals in the future of, what the actual integral of 1 over x is. So let's do logarithmic differentiation now, which is basically just taking all this ideas and making it more complicated. And it looks like I used a slightly different color, so bear with me on that. So logarithmic differentiation is basically just like, okay, I've got something really complicated. So in this case, our complicated thing is going to be y is equal to the square root of x times x to the fourth plus 3x squared plus 1 divided by, well, to the second divided by x to the fifth minus 1. So you would have to do like the product rule, somewhat the chain rule, definitely the quotient rule. You'd have to do a lot of work. And that would be just a pain. Like, I wouldn't want to do it. I don't think anyone else would do it. I'd probably mess it up like 5 times. So the way we get around that is by using logarithmic differentiation. So let's consider, like just using properties of logarithms. So let's take the ln of both sides. So we get the ln of y is equal to the ln of this mess right here, of this mess. So this is what we get. We just took the ln of both sides. But now we have ln inside right here, and we can actually use properties of logarithms to actually expand that and actually write it nicer for us to use. So this will be like, this is a product and this is like a quotient. So really this would be like, products become sums. So like ln of a times b is equal to ln of a plus ln of b, and like ln of like, c over d is equal to ln of c minus ln of d, just from those properties right there. And then just kind of working with the exponents as well. I want to erase those. So what we get is, ln of the square root of x times x to the fourth plus 3x squared plus 1 squared. That's just, a product, so you can just write it as a sum. And then x to the fifth minus 1 is on the bottom, so we just subtract that. And the fact is, typically those formulas are defined in pieces, but you can just do all of it at once. And the next thing we're going to do right here is we're just going to go ahead and simplify. So I'm just going to erase this real quick. We got to erase a few things before I rewrote over this. But, the next thing we're going to do is just, keep on simplifying. We're going to use more properties of logarithms to do some more work before we finally take a derivative. So, here we have the ln of the square root of x, but this is like, ln of x to the 1/2. But one of the properties of logarithms is that you can bring down that exponent, so it's equal to ln of x. So 1/2 ln of x. So that's what we're going to do here. So ln of the square root of x is equal to 1/2 ln of x. Now this has a 2 right here, so we can bring that down. So we get 2 times ln of x to the fourth plus 3x squared plus 1. And then x to the fifth minus 1 doesn't have anything in it, so we just leave this piece the same. And now we're going to be using implicit differentiation. So now we're going to take everything, and we're going to take the derivative of it with respect to x. And this is where it's implicit because, we have to use now we don't have just y, we actually have something as a function of y. We have y as like something other than itself normally. So in this case, we have ln of y. I remember that, the derivative of y is equal to dy dx. So kind of like what I said before, for the derivative of ln, it's 1 over the argument, so 1 over I, 1 over y, times the derivative of the argument, so times dy dx. And now this is where we get to use the properties of logarithms. So the derivative of 1/2 ln of x, derivative of ln of x is just 1 over x. So we get 1 over 2x. And then this is kind of where it gets kind of like what I told you before, where it has a mnemonic. So this thing is complicated. So what I say is, 1 over the argument. So, forget this real quick. I say 1 over the argument, x to the fourth plus 3x squared plus 1 times the derivative of the argument. So the derivative of the argument is going to be 4x cubed plus 3x. Oh no, 4x cubed plus 6x. Because the derivative of x to the fourth is just 4x cubed. Derivative of 3x squared is just going to be 6x. Derivative of 1 is 0, so it's not there. And remember that we still have this 2 out there, so that 2 comes down to here as well. And then lastly, what we have is, the derivative of the last piece. So negative ln of x to the fifth minus 1. So again, whoops, not what I wanted. 1 over the argument, so 1 over x to the fifth minus 1. And then to the top is 5x to the fourth. Because that's the derivative of x to the fifth minus 1. So all we did was, so far, is we took a complicated expression, we wanted to, take a derivative of it, but it seemed really hard, or not hard, but really just annoying. So we took the ln of both sides. We used the ln to break it up into nicer pieces. And then once we broke it up using the natural logarithm, we took a derivative with respect to x, and we had to use implicit differentiation, but that's okay. And that allowed us to actually break down the formula into being something nicer. So you notice that what we have right here is 1 over y times dy dx. And this expression right here is all in terms of x, so it's okay. So we need to move the y over because, again, we want dy dx. So that's all I did right here. Just move the y over. And then lastly, typically what you want to do is if you already have an expression of this form, technically if you take a derivative, the first thing you'll get is dy dx is equal to whatever the derivative of the inside is. So what that means is, like, one side you'll have just y's, on the other side you'll just have x's. So typically whenever you look at your final answer, you don't want it with a y in the answer. You don't want dy dx with a y in it. You would typically want to replace that with, like, what it actually is. So in this case, y is equal to this, the square root of x times x to the fourth plus 3x squared plus 1 squared divided by x to the fifth. So we plugged in for y, and we still multiply by the original thing. So that's that's it really. That's going to be our final answer. So it's not too complicated, After we took the derivative, all we did was just solve for dy dx. So we moved the y over, replaced what the y was, and that was it. And you wouldn't really need to simplify any of this. Like, you could just leave it like that, unless it was, like, super obvious. Like, if it was, like, the square root of 1 divided by 2, like, literally just square root of 1 divided by 2. If you did something like that, I'd be like, please simplify. But, if it's complicated like this, then you don't really have to worry about it. So there's some steps to do in logarithmic differentiation, and this is kind of like what I've just said. What you do is, like, take the ln of both sides of the equation, y is equal to f of x. Then we use the laws of logs to simplify with respect to, to just simplify. It's basically what we did beforehand. That way we had an expression that was broken up into sums and differences, and that because those are so much easier to take derivatives of. So the second piece is what we did was, we took the derivative, we differentiated implicitly with respect to x. And, that will give us, that 1 over y times dy dx term. Typically, that's what that's going to give us on the left-hand side. And remember that what that means is just with respect to. That's what with respect to? With respect to x. With respect to 2. But, once you do that, once you take the derivative, the next thing you have to do is just solve the resulting equation for y prime or dy dx. Typically you can use dy dx, sometimes you can use y prime, it just kind of depends on the situation. But logarithmic differentiation is also helpful when you have, equations of this form. So we have, y is equal to f of x and g of x. Well, y is equal to f of x raised to the g of x. So what that means is that the base and the exponents are functions. So this could be like, cosine of x raised to the cosine of x. Or like, e to the x raised to the 4x squared plus 2. It could be like that. So that in itself would be annoying, and we don't actually have rules to define those derivatives because it's not the product rule, it's not the quotient rule, it's not just a regular logarithm. So what we do is use logarithmic differentiation to actually find these derivatives. So an example is, we want to find y prime, where y is equal to sine of x raised to ln of x using logarithmic differentiation. So again, y is equal to sine of x raised to ln of x. So we're going to do the ln of both sides to get ln of the sine of x raised to the ln of x. And let me just erase, I'll just keep it like that. It looks weird. So all I did here with the next step over was I brought down the ln of x to get the ln of x here times ln of sine of x. And then now we take the derivative. So what I wrote was, d of dx everything. Take the derivative with respect to x for everything. So the left-hand side, the derivative of ln of y is going to be equal to 1 over the argument times the derivative of the argument. Like I said, y prime, but this is how I wrote it. So let me just write that in blue. You could also, maybe instead of doing, d of dx, you could just, prime it like that. But technically that's just like bad notation, really. Well, it's not bad notation, but it's not proper notation, but it's helpful to get you guys to understand what's going on. So again, you get, 1 over the argument, 1 over y times y prime is equal to, and now this is where we have to use the product rule. So we have, the derivative of ln of x times ln of sine of x. Those two functions are going to multiply together. So we have to use the product rule. So, keep the first one the same as what I normally do. So ln of x times the derivative of ln of sine of x. So 1 over the argument, 1 over sine of x, times the derivative of the argument. Derivative of sine of x is cosine of x, so that's how we get that. Then lastly, we have to do the derivative of the first piece. So derivative of ln of x is, 1 over x. We keep that the same. And then let me just draw some arrows. So, like that's pretty much it for that step, I guess. Just use the product rule. And again, this is kind of one of those things about the derivative of logarithms with the functions on the inside. Just 1 over the argument times the derivative of the argument. And likewise, how we did in this step right here is that we still had this y. We had 1 over a y, so we moved it over. And then we're going to substitute it back in. So that's what we're going to do here as well. So we get y prime is equal to, move the y over. I just put it right here. And remember that y is equal to sine of x raised to the ln of x. So even though I wrote it right there, it's because I think it just ran out of room. But I moved it to the left-hand side, so y prime would be equal to sine of x, ln of x, times all of this stuff. And all I did here was just simplify. Well, I didn't simplify, but I just combined some terms together. But, that's kind of it really for logarithmic derivatives. They're not too complicated, but it's just annoying to work with, and you just got to know the procedure, really. But the last thing we're going to do is we're going to do the number e as a limit. And this is kind of just fundamental stuff that kind of helps you understand what's going on, but it's not really required. But I'd still pay attention. So we want to express the number e as a limit, because if you remember how we defined e, oh yeah, e was the property, e was the function that was satisfied ln of a minus 1 divided by a, I think. I don't know. It was some weird inequality. It was some weird limit. It was some of the properties of exponentials. What I usually remember for the the limit definition of e will be the one we're doing here. So, kind of like what we've done so far is we have f of x is equal to ln of x. So we get f prime of x is equal to 1 over x, and f prime of 1 is equal to 1. So we're going to use that, we're going to use these facts, and we're going to use continuity of logarithms and exponentials to actually try to find the way we can express e. So what all of this means right here is that, f prime of 1 is equal to 1. What that means is 1 is equal to f prime of 1. And we're going to do the limit as x goes to 0 of 1 plus x minus 1, f of 1 plus x minus f of 1 divided by x. Typically what we do is we see h right here. So we get f of 1 plus h minus f of 1 divided by h, was h goes to 0. But honestly, variables are the letters are usually just placeholders for whatever we want to call them. So even though it looks a little weird here, we can do what we can do instead is by replacing that h with x and just kind of treat the inside as like a function of x. It's totally okay. So now we're just going to plug it into the function, f of x, well, ln of x. So we get the ln of 1 plus x minus ln of 1 divided by x. Ln of 1 is just equal to 0. So what we're going to do here is just ignore this step right here. We're just going to go ahead and try to rewrite the equation to get 1 is equal to the right-hand side. So is equal to just ln of 1 plus x divided by x. And then one of the properties of logarithms, remember, if you have like a times ln of b, this is equal to ln of b to the a. So really what we have is our a is equal to 1 over x and our b is equal to 1 plus x. So basically what that tells us that we're allowed to move that 1 over x. So really, because this is just 1 over x, and we can move that to right there. So that's what we did. So just so we get the limit as x goes to 0 of ln of 1 plus x 1 plus x raised to the 1 over x. So what we're going to do now is we're just going to exponentiate everything with respect to e. So we're going to raise everything to the e. And the fact is that this doesn't change anything. E is actually a very nice one-to-one function. And limits are continuous, logarithms are continuous. So basically what this tells us is that this behaves pretty nicely. So what do we get? Is we get e to the 1, so e to the 1 right here is equal to e raised to the limit. So e raised to this. And now this is actually where we're going to use properties of continuity, is that, one of the things of properties of continuity is the limit as x goes to, say, let's say the limit as h goes to x of f of x is equal to the limit, is equal to, f of the limit as h goes to x. So basically what that tells us is that, we can pull the limit outside the function as much as we can pull it inside the function. So e of the x is continuous. So I'll write, as e of the x is continuous, we can pull out the limit. I'm writing that just so you guys know and just to be kind of clear. Sorry about the messy handwriting, I'm just kind of writing fast. So we can pull down the limit, bring it down. This is how we get to this step. And now what we can do is just those properties of logarithms that we like so much. E to the ln of x, that's just equal to x because they're inverse functions. So what we get is just the argument comes down. So we get the limit as x goes to 0 of 1 plus x raised to the 1 over x. So what that tells us is that, this right here is e to the 1, but that's just e. So we get e is equal to the limit as x goes to 0, 1 plus x raised to the 1 over x. And the more common way I see it typically is x is equal to 1 over n. Or, okay, so let me just kind of clarify real quick. This right here is another definition for e, but typically, it's a very nice definition actually. And it's pretty helpful in some certain situations, but we can do a substitution. So we can do x is equal to 1 over n. So thus as x goes to 0, this would go to 0. So we need 1 over n to go to 0, but that's the same thing as just n going to infinity. So we're basically just doing a change of variables. In this case, when we do a change of variables, we still want to go to the same place. X will have to go to 0, and we'll have to go to infinity. So we have the limit as n goes to infinity of 1 plus 1 over n, because that's what we're plugging it in. So 1 over x will just equal to 1 over 1 over n, which is just n. So this is actually the first definition of e that I've ever heard of, I think. This actually comes from interest that has a lot of history behind it. This is the first definition of e, whereas it showed up in history actually. It's pretty cool though. E shows up in so many places. It's a beautiful thing. But actually, that's it for this section. Hope you guys liked the video. I hope I managed to cut down times a bit. Let me know if you have any feedback, of course. But thank you for watching. Like, comment, and subscribe.